Post-tensioning design basics. In this presentation, I will take you through some of the basics of post-tensioning design, become familiar with different design options. I will talk about load balancing, why and where secondary actions, secondary moments are used, find out more about beneficials of post-tensioning, where it is beneficial and where it is detrimental, talk about pre-compression and effective width, identify where post-tensioning could be detrimental. Now, starting with design requirements of a post-tension structure, universally, the design requirements address serviceability as one design step, then address safety as a second design step, and finally, initial condition, that is transfer of pre-stressing to the member. Now, the combinations for the safety include the effects of hyperstatic action and obviously the effects of post-tensioning, and that is something which is one of the focuses of the presentation today. The design options are three, and they are based all on the factor of making sure that the structure meets the safety demand. The three methods are straight method, load balancing, and comprehensive method. The features of these three methods are detailed in a different presentation. This presentation right now that we are going through focuses on load balancing, the second option. Now, what are the differentiating consideration above the three post-tensioning design options? In the straight method, the post-tensioning is considered as an applied load for service condition and as an applied load for safety condition. You know, we have safety, serviceability, and initial condition. In load balancing, post-tensioning is viewed as an applied load to the structure for service condition design and as a resisting member for safety condition design. Differs in the way the post-tensioning is accounted for between the two methods. In the comprehensive method, the post-tensioning is viewed as a resisting member in service condition and as a resisting member in safety condition. So it is considered to be on the resistant side. You know, you have the demand side and the resistance side. In the comprehensive method, it was on the resistance side in both cases. It is interesting to note that until around 1950s, the only method available was comprehensive method, method 3, which was developed in Europe and was the only method. It is difficult to do. It is a little complex in computation, and that probably was one reason why post-tensioning was widely used. Around early 1960s, this second method, load balancing, was introduced, which is much simpler, simplifies the calculation, and is, in my opinion, the major factor in increased use of post-tensioning. The third method, straight method, was introduced I think 2 or 3 years ago. I have the reference of it. It's published in Structures magazine. It is very simple, but since it is very new, has not yet been adopted much. Now, today in this presentation, I'll focus on load balancing. Load balancing comes in its simple format, which was introduced in 1963 by T.Y. Lin. It was applied or applies to many structures, but was not universally applicable, and that is why it was not used in bridge constructions and where sections were not of uniform cross section. It was extended in 1990 to make it applicable to all structures, and today that is the primary method of use. Now let us start with simple load balancing. In simple load balancing, if you have a post-tension member as shown here, you assume that the tendon is taken out of the member as shown on the right, and obviously it has its forces which keeps the tendon in equilibrium in order to restore the condition of the original structure in calculation of deflections and stresses. You put back the forces from the tendon that result in bending. This upward force is put back in the member, and obviously the reactions here. And then you separate the axial force, here shown on the bottom right, and we argue that the axial force in simple load balancing results in uniform precompression, doesn't need any sophisticated calculation, and whatever we have on the left results in bending, as engineers knew it well and could handle it well, moments and shears and so on. So it was a method to which the engineers were familiar, and it resulted in a widespread use of the technology, but it was based on the fact that the separation resulted in the diagram as I show on the bottom right, which is uniform pre-compression. Uniform pre-compression as shown at bottom left. So simple load balancing is based on constant force and decoupling of axial and bending effects. Now, if the post-tensioning tendon is somewhat complex, didn't matter. It is broken down into segments, each applying a force up or down depending on the geometry of the tendon. But the concept is the same. The axial force is assumed constant and uniform, irrespective of the shape of the tendon. It is assumed that the tendon acts at the centroid of the member. That is very important. That is the core of simple load balancing. Now, let us view quickly the extended load balancing, which is now in common use. If you have a member which has a step in it, is not prismatic, the post-tensioning that is acting or is anchored at one end does not line up with the post-tensioning with the other anchor at the other end, because the centroids are not aligned. So this lack of alignment results in a bending moment in the member. This contradicts the basic assumption, primary assumption of simple load balancing, that the bending is separated from the axial. The figure shows the change in centroidal axis, and they remove the tendon. The forces do not line up. That results in bending moment. So this requires a modification in our basic assumptions. Here I show you a member, section of the member where there is a change in cross-section. The way it was proposed to handle is shown at top right. At the change in cross-section, two couples are introduced, one counterclockwise, one clockwise, equal and opposite. Because the two couples are equal and opposite, it does not disturb the equilibrium of the system. One of the couples is considered to act with the centroidal forces at the ends and result in a uniform precompression, and the other couple, which causes bending, is added to the bending effects. So the premise of load balancing, that the bending is separated from axial, will be reestablished by introducing a couple at the location where there is a change in centroid. Here in these two images, I show you the couple on the left resulting in uniform precompression, and the same value of the couple added in the right for bending effects. So this results in uniform compression. The equilibrium of the moment is retained. Now let us talk a little bit about hyperstatic actions. When load balancing is used, it requires the hyperstatic actions to be extracted and accounted for in the safety consideration of the member. The following gives the reason why we have to extract the hyperstatic actions and account for them in the safety. Why hyperstatic actions should be calculated separately. This is a very straightforward demonstration. Over the years, I have gone through 8-9 different presentations of hyperstatic actions, and what I'm going to go through now is the latest, which I believe is the most easy, or is the easiest to explain the phenomenon. When you look at the load balancing of the building codes, you have the service condition load balancing, and you have the you have the service condition load combination, and you have the safety load combination. I like you to note that in the load combinations, K1, K2, K3 are coefficients given in the code, but what you add is dead load value, moment, live load value, and so on. Dead load is remains the same in both. The coefficient has changed. Live load is the same live load, but the coefficient is changed. But the post-tensioning is not the same. The value you enter for post-tensioning in the service condition is different from the value you enter for post-tensioning in the safety condition. Not so for dead and live. And here is what is the reason. By the way, before I go to the reason, this feature is because we are using the load balancing method of design. If you use the simple method of design, these two will also be the same. You don't have the hyperstatic here, you have PT here. But now the focus of this presentation is load balancing. So let us concentrate on the hyperstatic item. It says K1 and K5 are different, and let us know why they are different. Before going into the explanation, I want to show one or two slides. The objective of this one or two slides is to prepare you mentally to receive or to accept the slides that relate to hyperstatic action. So it is not related to hyperstatic directly, but it is just in preparation. Here there is a member which is strong in compression, weak in tension. It is extreme representation of concrete, with the difference that zero tension capacity is the property. Assume that it is supported on simple spans rollers all along except the end, has a post-tensioning tendon through its center, pulled and anchored. Now the question that I have is, will this member break into two if we remove the supports? Based on your intuition, you will say obviously, because the member has weight and it bends down, because it cannot develop tension, it will break down. So you know the answer, but I'm going to give the answer approaching differently, because this is the focus is on the approach in getting the answer, not the answer itself, because the answer is straightforward. What we will do is we will try to envisage the failure and then determine what is going to be the demand at the face of the failure and what is going to be the capacity of the member at the face of the failure. If the member cannot develop adequate capacity for the demand, then it fails. Otherwise, there is no reason for it to fail. In order to do so, in order to determine this, I will make a cut somewhere along the member. What you see here is a cut from the left. And when I make a cut, on the right, I first calculate the demand. And then on the right, I look at the face of the section and look and see whether resistance adequate for the demand can develop. If it can, then it's good shape. Now look at the right. The demand, we know from our courses, for a member like this is a shear, axial, and moment. What are these? Here is the critical pause. I like you to answer. What are these? I say moment is 0, shear is 0, axial is 0. Why? Because I calculate the demand not looking at the supply, looking at the cut structure. See, what are the forces at the cut structure that will result a demand at the section? all the vertical goes down to the support. The force which is anchored here goes directly to the member. There is nothing on the left, which will contribute to the demand. Therefore, there is no requirement for resistance to be developed at the face. In this case, does it mean that there will be no stresses at the face? No. At the face, I have this post-tensioning tendon, which will result in stresses. But they are in equilibrium. They are in equilibrium like the one on the right is in equilibrium. So the answer is no, this member will not fail, irrespective of the amount of post-tensioning. It may crush if the force of post-tensioning is too high, but it will not break in the sense that we say it will fall into two pieces. If the demand at the bottom right, I say if the demand is greater than the resistance that can develop at the cut, the member will break. In this case, the member will not break into two. Good. Now let us look at this member here. I have a member here which is floating in the air, weightless member floating in the air. The question that I raise is this member going to break at section AA? Will it break at section AA? We use the same method. The method of the previous section is to cut the structure into two and find the demand and look at the capacity. If I cut it into two, is there any force demand here at section AA? You would say no, because there is nothing on the right. I said it is weightless and it has no forces acting on it. So there is no demand here. As a result, there is no reason for this member to break. Fine. It will change its shape if it is if its temperature is raised or lowered, but it will not break into two. Fine. Now I am going to apply a load on the member, but the loads are in equilibrium, add up to zero. Weightless object in equilibrium, and it is floating. I raise the same question. Is it going to break at section AA if I increase the load? You would use the same scheme of analysis. You would say, let me see whether there is a demand here. You would say, these external forces can result in a movement and shear here, and the section must develop on the resisting side compression and tension to resist the moment. So your answer is, in this case, when I have forces acting on the cut section, even though the entire is in equilibrium, but the section cut may not be, therefore I require a resistance here for encountering the demand. Fine. Now I go to post-tensioning. There's a member that is post-tensioned but has no weight, weightless member, and I keep on, it is floating in the air, and I keep on increasing the force in post-tensioning. I ask the question, is it going to break at AA if I keep on increasing the post-tensioning? You would say you followed the same scheme. you break it at AA and you try to determine the demand at the cut. The critical question is there a demand at the cut due to the forces on the right? Remember the introductory example we had a couple of slides back? The answer is no. There is no demand here at the cut, irrespective of the shape and force in the post-tensioning. Because there is no demand, there will be no break of the section. Then what happens if I continue to increase the force more and more and more? The section will crack, as I'm showing at the bottom, because tension will develop on the part of the section. It is possible, depending on the location of the tendon, there can be tension. Tension will develop, and as I increase the force, crack will result in increase in its depth, and it stops. The crack depth stops when the centroid of the tendon falls within the kern of the section. You might remember from courses in your mechanics of solids that each section has a kern, 1/3 if it is rectangular, and if the force is within the kern, it will develop only compression. It doesn't develop tension. So the members will crack, and the depth of the crack will extend to the point to make the centroid of the tendon at the kern. So we have cracking, not failure. Then, in conclusion, post-tensioning in a member on its own cannot result in the member failure. Member failure is associated with what we call the safety check of the design process. Cracking is the serviceability check of the design. For in cracking, you calculate stresses, not when it comes to safety. So what we do here, it says that the cracks will widen to a maximum depth. Then you bring the argument that the post-tension members we handle daily do not float in the air. They are supported on columns and walls, beams, as I have shown here. Now this is a member that is intended to represent the real condition, supported. And the question is the same. Does this member break into two if we increase the post-tensioning? We do the same, we go through the same steps. We will cut it at section AA. We will cut it at section AA, and if we cut it at section AA, then before cutting it, I've just mentioned that if its temperature is increased, it will change its shape. But that's another issue. But if we cut it at AA, now I have cut the section at AA. At AA, the post-tensioning force tends to flex the member, and because the member is not free to move at all points along its length, at the connection to the supports, the member is held in position. The member moves elsewhere, but not at the supports. As a result, you develop reactions at the supports because of constraint of the member. Now, going back, the reactions at the support, if I make a cut, will cause a demand. This and this cause a moment at this point. It is the reactions which result in a demand, shown in red here, and the demand will in itself call for resistance. In conclusion, the demand is caused by these reactions whenever post-tensioning member results in reactions. And when does it result in reactions? When the member is not permitted to deform under the force of post-tensioning. These reactions cause demand, and the demand has to be met by the resistance of the support. Member is safe if the force, demand, hyperstatic moment can be resisted by the actions developed at the face of the cut. So in a post-tension member, demand for resistance at the section develops only if the member is not free to deform, namely in statically indeterminate structures. That is why it is called hyperstatic. In summary, in service condition, where we have deflection and stresses and cracking, we use the up and down forces of the post-tensioning. For safety, we use the hyperstatic actions, and those are from the reactions of the post-tensioning. Here at the top right, I have taken just a simple member supported on 3 points to be hyperstatic. If you take the strand tendon out, you will have the up and down forces. This is the simple load balancing. This is what introduced in 1963, substituting the comprehensive method which was prevailing until then. But if you recognize that there is a change in section and there is also a bending moment, combination of this and this will be the, so to say, extended load balancing, and will be used to calculate the deflection and the possibility of crack formation. But if you recognize that the combination of these two will result in what I'm showing at the bottom, these reactions will cause moments and shears in the member, and these will be used in the safety of the structure. For serviceability, these will be used, all of them will be used for serviceability, BCD. For safety, this will be used. Good. Now that we know about hyperstatic, how hyperstatic actions are calculated. The standard method of calculation, the universal method of calculation, which applies to slabs, multi-story, bridges, everything, is the direct method. The direct method says, find the reactions from post-tensioning, apply the reactions to the member, and calculate the demand. The direct method is universally used, and I show you a detailed example of it. In the direct method, you analyze the structure shown on the top, you calculate the moment and shear from post-tensioning, then you apply the moment and shear from post-tensioning to the member, and at a section like here, you would say the hyperstatic moment and hyperstatic reaction is the sum of these moments and force times distance. This is the expression at the bottom. This is how it is done, and it applies to all situations. It applies to slabs, and it applies to multi-story buildings. For example, if you have a slab like this, you put a load on it, post-tensioning on it, you put the post-tensioning on it, you calculate from the post-tensioning the support reactions. These are the support reactions. Then you create a new system matrix, a totally new solution in which you apply the reactions at the bottom of the columns to this new structure. And the solution will be the hyperstatic. So you solve the problem 2 times and it is very important because the hyperstatic reactions must be in self-equilibrium. Otherwise, you will not be able to obtain a mathematical solution. When you apply a number of forces to a structure in space, unless these forces if you apply a number of forces to a space structure which is not supported, it's just floating, the forces must be in equilibrium, otherwise the structure floats. And that is a condition which must apply here. The reactions must be in self-equilibrium, otherwise it will not work. That means you have to have a software or a formulation that is reliable and works. Good. That is how the values are obtained using secondary solution. I have shown here from the direct method the reactions. These are the reactions, and this is the bending moment in the slab obtained from the direct method. Everything must be in self-equilibrium. The hyperstatic forces must also be in self-equilibrium. Everything must be in self-equilibrium because the tendon itself is in self-equilibrium, irrespective of its shape, irrespective of its force. Tendons are always in self-equilibrium. Now, is this the method that our fellow engineers use daily to calculate hyperstatic reactions for their daily design? I would say if you use a well-documented computer program, no. But in the past, until recently, when this direct method was promoted and included in computer programs, some computer programs, others used what we call indirect method. And you may be familiar with indirect method. Indirect method is a simplified method which applies to prismatic structures. And the way it works, it says at any section, the hyperstatic moment is equal to the balanced moment. Balanced moment is a moment from post-tensioning, MB, minus post-tensioning force times distance of the tendon to centroid. This is a simple formula which works well for problems as I am showing you on the right. And I am showing to you how this formula, the indirect method, is arrived at. Basically, you can look at it at your leisure, but the way it works is that the tendon is removed, the forces from the tendon, up and down forces and axial, are shown in the member. These same forces are acting on the tendon. These two are in equilibrium, and then they are equal and opposite. The forces that I have shown here will result in bending of the member on the top, and the bending of the member on the top will result in generation of reactions. And that is what we have been talking about, hyperstatic reaction. They result in reactions. Now, the reactions will cause hyperstatic moments. That is what we have been talking about. If you look at the top right, I am showing you the forces from the tendon at a cut. I am not showing you the reactions here, but because it is supported, it is shown here. If I support this member as it is in real life, there would be a reaction here and there would be a reaction here. Otherwise, the applied force is in equilibrium here. The tendon force is in equilibrium here. But the reaction due to movement here will cause a different bending moment here. P, that is the hyperstatic here, P sub x. And the way I have worked it out, I calculate the hyperstatic moment here from this diagram by simply taking moment of the forces. I show everything here one more time. These are the reactions which are hyperstatic reactions versus the hyperstatic moment. So this is a definition that the primary moment is tendon force times eccentricity. This is just the definition. And looking at B, I don't want to go into its great detail. Here you can look at it at your leisure. This force times this distance is equal to this value based on the diagram. And from C here, I have another value by taking moments here. I will get this expression, compare these together, and by definition, this is the hyperstatic moment. Reactions times distance are the hyperstatic moment, and this can simplify to this, can simplify to the hyperstatic moment being the balanced moment minus PE. This has been in common use by many of our fellow engineers, and they still use it, and it applies well to the configuration that I showed you here for prismatic members. That brings me to the closure of this part of the presentation. What did we cover? We talked about design requirements, which was safety, serviceability, initial condition. Talked about design options, which is a straight method, load balancing, comprehensive method, but we concentrated on load balancing. And in load balancing, we started with simple, where there was no change in centroid. And then we talked about the impact of change in centroid. Then the presentation of why hyperstatic moment comes into strength calculation. We have to bring it into strength calculation, and then how to calculate hyperstatic moment. There are other critical issues, which is the extension of this presentation. Those I have compiled in another presentation, presentation 26. Thank you for being patient and following this presentation.